Hello, welcome to section 1.5. Today we're going to talk about equations. First, let's start with a few definitions. An equation is a statement that two expressions are equal. The values of the variables in the equation that make the equation true are called solutions or roots. The process of finding the solutions is called solving the equation. Two equations with the same solutions are called equivalent equations. In a bit here, we're going to talk about how to solve an equation. What we're going to do is use a sequence of equivalent equations in order to find the solution to all of them. But first, let's talk about the properties of equality. A equals B if and only if A plus C equals B plus C. Adding the same quantity on both sides preserves equality. Now that goes for subtraction as well. A equals B if and only if C times A equals C times B. Multiplying the same quantity to both sides preserves equality. Now that goes for division as well, because division is just multiplying by a fraction. Let's do an example. Suppose 3x equals 12, then A, 3x plus 5 equals 12 plus 5. This is the preservation of equality under addition. And 2 times 3x is equal to 2 times 12. This is preservation under multiplication. Now, in part A, what we would then have is 3x plus 5 is equal to 17. What we're saying here is that 3x plus 5 equals 17 is an equivalent equation to 3x equals 12. They have the same solution set because equality is preserved under addition. Similarly, 6x equals 24 is also an equivalent equation. For the same reasons, but multiplication instead of addition. The next thing we're going to talk about is solving linear equations. A linear equation has the form ax plus b equals 0, where a and b are real numbers and x is a variable. Now, a similar equation, ax plus b equals c, is also linear. In order to get it into the form in the definition here, all we have to do is subtract c, and then we have ax plus b minus c is equal to 0. Now this is in the previous form, even though your b and your b minus c don't exactly match up. So we have a b minus c here and a b here. They don't exactly match up, but it doesn't matter because all we're saying here is that b is a real number, and b minus c would also be a real number. So it would still hold the form of a linear equation. It's a different form when it looks like this, but it is still a linear equation. Example, solve the equation. So here we have an equation, 4x plus 5. Now whenever we're looking to solve an equation, generally we're looking to do it in reverse order of operations. We want to get rid of the 5 first, and then we'll worry about getting rid of the 4. Now our end goal is to get x alone on one side of the equality, so that we know what x will be equal to. That will be our solution. So an equivalent equation will be 4x plus 5 minus 5 is equal to 17 minus 5. Now here all I did was subtract 5 from both sides. Now I specifically chose 5 because 5 minus 5 will be 0, and I'll eliminate the constant that I have here. So I'm left with 4x is equal to 12. Now this is an equivalent equation. It'll have the same solution set as we noted before. When we subtract a number from both sides, the equality is preserved. So now what I need to do is I need to get rid of this 4. Well, I can multiply both sides by 1/4. And the 1/4 and the 4 will cancel out because 1/4 is the inverse of 4 under multiplication. And then 12 times 1/4 is actually 3. So our solution is x equals 3, which is an equivalent equation to the original equation that we had. Notice that we used a sequence of equivalent equations. We started with 4x plus 5 equals 17. we went to 4x equals 12 when we subtracted 5 from both sides. This is still an equivalent equation. And then we ended with x equals 3, also an equivalent equation. We used a sequence of equivalent equations in order to get to the solution. Try one. Solve the equation. 12x minus 3 is equal to 3. Now what we're going to talk about next is equations with multiple variables. Now in this section, in this class, all we're looking to do is isolate a single variable, one that's specified in the question. So if we had something, say we had something that looks like this, and we're looking to solve f equals g times capital N times lowercase m divided by r squared for capital G. Now, if you don't recognize this equation, it's a gravity equation. Force is equal to this gravity, where g is the gravitational constant, capital M is the mass of one of the objects, lowercase m is the mass of the other object, and r is the distance between the two. So we're looking to solve for the gravitational constant g. So in order to do this, what I need to do is I need to isolate g on one side. Let me write it down here. What I'm going to do first is I'm going to eliminate the r squared. What I want to do in order to eliminate the r squared is figure out what the inverse of it is. Now this is 1 divided by r squared. What would the inverse of 1 divided by r squared be under the operation of multiplication? R squared. If we multiply by r squared, it will cancel out the r squared in the denominator here. So we're going to multiply both sides by r squared. We get the cancellation on the right that we want. And then on the left, we're left with f times r squared. On the right, we're left with g times capital M times lowercase m. Now, in order to eliminate capital M and lowercase m, we're going to divide both sides by m and lowercase m. Specifically, what I'm going to do is multiply by 1 over capital M and 1 over lowercase m. So both sides, we get something that looks like this. And then when we simplify, of course, the capital and the lowercase m cancel on the right. And then on the left, we're left with just capital and lowercase m. Nothing happens to them. They just end in the denominator here. And we're left with g on the right. This is an equivalent equation to our starting equation. It's just in a different form. Try one. The volume of the Death Star's main reactor is given by V equals 2/3 pi times r squared times h. Solve for h. The next thing I want to talk about is solving quadratic equations. A quadratic equation is an equation of the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers with a not equal to 0, and x is the variable. The zero product property plays an important role in solving quadratic equations. What it says is that if the product a times b is equal to 0, then either a is equal to 0 or b is equal to 0, or both. But one of them has to be 0 in order for a times b to be 0. And if you want to, you can verify this by trying to think of two non-zero numbers that would multiply to 0. And it will obviously be impossible. Let's do an example. Solve the equation for x. So if we have the equation x squared minus 5x equals 24, then what we want to do is we want to get all of the terms on one side first to put it in the proper form. So it'll look like this. All I did to get from this step to this step is subtract both sides by 24. Now what I'm going to do is factor. Now we have some experience factoring from the previous sections. We need to multiply to 24, specifically negative 24, and add to negative 5. So two numbers that multiply to negative 24 and add to negative 5 will be negative 8 and positive 3. Now since our a in this case is equal to 1, we can go straight to the factorization. And notice what happens here. We get x minus 8 times x plus 3 is equal to 0. Notice that we have a product of two things that is equal to 0. What does that mean? Well, by the zero product property, that means that at least one of them must be 0. So we get that x minus 8 is equal to 0, or x plus 3 is equal to 0. So we have to solve for both values of x, because both values of x will create a product of 0 within this multiplication. So once we add the 8 over, we end up with x equals 8, and on the second equation, we get x is equal to negative 3 by subtracting 3 to both sides. Now, both of these are solutions to the quadratic equation. Notice if we plug in 8 for x, we get 8 minus 8, which is 0, times 8 plus 3, which is 11. But we would have a 0 times 11, which will give us 0. And if we plug in negative 3, we would have negative 3 minus 8, which is negative 11. But we would also have negative 3 plus 3, which is 0. So we'd have negative 11 times 0, which is also 0, which does satisfy the equation, therefore is a solution. Try one. Solve the equation for x. 2x squared minus 3x minus 14 equals 0. Notice that your a is not equal to 1, so you will have to use the long version of the factorization process. The next thing I want to talk about is solving simple quadratic equations. Now there's going to be two ways that I solve this. Both will give us the same answer, but I want to show you how the math lines up. The solutions to x squared equals c are x equals the square root of c and x equals negative square root c, provided that c is greater than or equal to 0. Now, c needs to be greater than or equal to 0 whenever we have a even index on a radical. Now, since we're dealing with quadratics, in this particular case, we have an even index. But this won't always be the case as we move forward through the class. Recall the difference of squares. A plus b times a minus b is equal to a squared minus b squared. Now, specifically what we're going to do here is we're going to go from the right side to the left side. So suppose that we're given x squared equals c. This then implies that we can subtract the c to the other side and get an equivalent equation. X squared minus c is equal to 0. Now if we treat c as if it's a square, and it is, x squared minus the square root of c squared equals 0, then we have a difference of squares, and this factors. X plus square root c times x minus square root c, which is equal to 0. So far we have a sequence of equivalent equations. Now we also have the zero product property in this case. We have x plus the square root of c times x minus the square root of c is equal to 0. This then means that x plus square root of c is equal to 0, or x minus the square root of c is equal to 0. So we solve each equation, and we get x is equal to the negative square root of c, or x equals the positive square root of c. And these will be our two solutions. This is how we get the solutions in the top. Now, the other way to go about this is actually just taking the square root of both sides. Now, many of you, when taking the square root of both sides, have probably learned the rule that you need to add the plus or minus. But this becomes confusing when taking square roots later on. So suppose that we have this. So let's go ahead and take the square root of both sides. So we end up with the square root of x squared equals the square root of c. Now you have to remember that the square root of x squared is not x, it's the absolute value of x. So we end up with the absolute value of x is equal to the square root of c. Notice I haven't added the plus or minus yet. Now there's a reason for that. When you take the square root of c, you don't add a plus or minus. Where the plus or minus comes in is when we have the absolute value of x is equal to the square root of c. Because this then means that x is either going to be the square root of c or x is going to be the negative square root of c. What we're saying here is that x's distance from 0 is the square root of c. So if we look on a number line and we add 0 in the middle, we have the square root of c here, and we have a square root of c here. The one on the right is positive square root c, and the one on the left is negative square root c. Well, we know that the absolute value of x has this distance. So we know that x is either going to be here, or x is going to be here. Either way, it has a distance of square root of c from 0. Further notice that if we plug in a square root of c into the absolute value bars, we get the square root of c. If we plug in a negative square root of c into the absolute value bars, we also get the square root of c. So that we can see that both of these equations are actually true. Thus, they're both solutions to the equation itself. Try one. Solve the equation. X minus 3 quantity squared equals 4. Okay, the next thing that I want to talk about is completing the square. This is a very important topic. Recall, a plus b quantity squared is equal to a squared plus 2ab plus b squared. Now I'm going to make a note here. X plus b over 2 quantity squared. Now, if we pattern match, x is our a, b over 2 is our b, then what we get is x squared plus bx plus b over 2 quantity squared. So I want you to notice something. Suppose that we had something that looks like this, x squared plus bx. Now, what I want to do is I want to make this look like x plus b over 2 quantity squared. Something of this form where we have x plus something squared. Since I have a bx, what I actually need to do is add b over 2 squared. So if I can add b over 2 squared, then this will factor into x plus b over 2 quantity squared. Okay, that is the end goal. That's what we're trying to do. Okay, as a visualization, I'm going to show you what this looks like as a square here. So suppose we have this square here, and then we have if this is x, this is b over 2, this is the same, b over 2, and this is x. So this entire side length is x plus b over 2. This entire side length is x plus b over 2. We have a square here. So if we multiply them, we would get the area. Well, this area here is x times b over 2. This area is x times b over 2. And this area is x squared. So if we add up all of the areas in here that we have, then we should get x plus b over 2 quantity squared. What we're missing is this piece, the b over 2 squared. This is what we need in order to complete the square. Let's do an example. I'm going to walk you through this process. Complete the square and solve for x. X squared plus 6x plus 8 is equal to 0. Now there's a couple of ways that we can go about this type of problem. One is the very common way, subtract the 8 to the other side and keep the x squared plus 6x on the side alone. Now I'm going to leave a space because we want to complete the square, but I subtract the 8 to the right. Right, now what goes in this space is the b over 2 squared. What I need to add here is b over 2 squared, where our b is 6. So if we take 6, divide it by 2, we get 3, and then we square that. So we do 3 squared, then we need to add 9 to the left side. But what that does is it tips the scale on our equation. It makes one side no longer equal to the other. So in order to keep the scale the same, I add 9 to the other side as well. So now I have x squared plus 6x plus 9, which we will use to factor into x plus 3 quantity squared on the left, and then on the right, negative 8 plus 9 is of course equal to 1. Then to solve the equation, you can take the square root of both sides, or you could subtract the 1 over and do a difference of squares. I'm a little bit more partial to doing the difference of squares, but for the sake of simplicity and for the sake of the majority of people, because I'm a weird mathematician, I'm going to take the square root of both sides. So we end up with x plus 3 in absolute value is equal to the square root of 1. Now the square root of 1 is 1. We would then get x plus 3 is equal to 1, or x plus 3 is equal to negative 1. What that is to say is that if I replace x plus 3 in my absolute value with 1, then I'll get 1, which is the same thing as square root of 1, of course. Or if I replace x plus 3 with negative 1 in my absolute value, I also get 1. Both of these equations serve to find a single solution for this equation. So in the first one, we get x plus 3 is equal to 1, will yield x is equal to negative 2 by subtracting 3 to both sides. And then subtracting 3 to both sides in the second equation gives us a negative 4. Both of these solutions satisfy this equation, which should satisfy this equation. Now we can check them. Plug in negative 2. Negative 2 squared is 4 plus 6 times negative 2. This would become negative 12. So we'd have 4 minus 12 plus 8. And that is equal to 0. Similarly, if we plug in negative 4, we would have 16 minus 24 plus 8, which also gives us 0. So both of these are solutions to the equation. Now the other way to do this is sort of sidestepping this step here a little bit. I think this way might be a little bit better in the long run, but it's not necessary right now. If we take the 8 into consideration when we complete the square, then we don't need to subtract it to the other side. Okay, I'm going to leave my 8 over here, and I'm going to put it on a line like this. It's still equal to 0. Now, we're only looking at these two terms here, x squared plus 6x. How do I complete the square? You divide your b by 2. So 6 divided by 2 is 3, and 3 squared is 9. So I need my line to contain 9, but right now it only has 8. So instead of subtracting the 8 to the other side and adding 9, what I'm going to do is keep the 8 there, and I'm going to add the number that I need in order to get to 9. So I need to add 1. Now I add 1 to the other side as well to keep the equation balanced. Then I end up with x squared plus 6x plus 9 is equal to 1, and we can factor from there. X plus 3, quantity squared is equal to 1, and then we have the same solution as we had before. All right, I want you to try one. Complete the square and solve for x. X squared minus 12x is equal to 64. Now you should get two solutions here. I'm just warning you. All right, the next thing that I want to talk about is the quadratic formula. The roots of the quadratic equation ax squared plus bx plus c equals 0, where a is not equal to 0, are x equals negative b plus or minus the square root b squared minus 4ac all over 2a. I want to note here, x is solved for when using the quadratic formula. So the next thing I'm going to do, I'm going to prove this really quickly. If you don't want to see the proof, that's okay. Skip to the next example. We prove this by using the completing the square method. So we start with ax squared plus bx plus c equals 0. First thing I'm going to do is I'm going to subtract my c to the other side. And then I'm going to factor an a out and divide it to both sides. I'm doing this because when we complete the square, the coefficient on the x squared term needs to be 1. So now to complete the square, I do b over a divided by 2 and square that. And I need to add that to both sides. So we'll have b over 2a quantity squared, and we have to add that to the other side as well, and we get this. Then the left side factors very nicely into x plus b over 2a quantity squared. On the right, when we square the b over 2a and we add the two like terms, and we add the fractions, we will end up with b squared minus 4ac over 4a squared. Now to solve, what we do is we take the square root of both sides, of course, x plus b over 2a. Now this would normally be an absolute value. I'm going to skip that and just go straight to the plus or minus on the right. Plus or minus square root b squared minus 4ac over 4a squared. Now if you remember, we can actually take the square root of the top and the bottom separately when we have a fraction under a radical. Taking the square root of the bottom will help because it's just going to be 2a. So we end up with x plus b over 2a is equal to plus or minus square root b squared minus 4ac over 2a. And then we subtract our b over 2a over and combine the fractions. They already have a common denominator, so we end up with x is equal to negative b plus or minus square root b squared minus 4ac all over 2a. And that will complete the proof. So the very next thing we're going to do is an example to show how the quadratic equation works. Use the quadratic formula to solve the equation. Right here, our a is equal to 3, our b is equal to negative 4, and our c is equal to negative 7. So if we use the quadratic formula, we have x is equal to, don't forget this part, x is equal to the quadratic formula. So our b is already negative, so we'll end up with a positive 4 plus or minus the square root of b squared, 16, minus 4 times a times c. So 4 times 3 times negative 7. Let me write that out first. And then we'll do the multiplication. All divided by 2 times a. So we get 4 plus or minus the square root of 16 plus 84 all over 6. Now 16 plus 84 is of course 100. The square root of 100 is 10. So this will then become 4 plus or minus the square root of 100 over 6, which is 4 plus or minus 10 over 6. So I want to note here, this is very, very important. There are two solutions here. X is equal to 4 plus 10 divided by 6, and x is equal to 4 minus 10 divided by 6. So we have x is equal to 4 plus 10 all over 6, and x is equal to 4 minus 10 all over 6. Now 4 minus 10 over 6, that would be negative 6 over 6, which is negative 1. And x equals 4 plus 10 divided by 6 will be 7 over 3. 14 divided by 6 reduces to 7 over 3. These will be our two solutions for this example. Definition. The discriminant of the general quadratic equation ax squared plus bx plus c, where a is non-zero, is d is equal to b squared minus 4ac. Now this number should look very familiar, specifically because it's a part of the quadratic formula. 1. If d is greater than 0, then there exists two distinct real solutions. If d is equal to 0, then there exists one real solution. If d is less than 0, then the equation has no real solutions. We'll deal with the no real solutions case in the next section, where we'll have complex solutions. But for right now, we're just going to say that it has no real solutions. Now, I want you to recall the quadratic formula. I know it was a very long time ago, but let's think back real hard and remember what it is. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Notice that the discriminant is a part of the quadratic formula. Specifically, it's the radicand. What's under the radical? Now think about this. Think about this. B plus or minus this number. So if the discriminant is positive, then we have negative b plus or minus a number divided by 2a, meaning that negative will have two solutions because negative b plus that number and negative b minus that number will generate two distinct real solutions. However, if d is equal to 0, then we only get a single solution. Why? Because negative b plus 0 is the same as negative b minus 0. So if d is equal to 0, the square root becomes the square root of 0, which is 0. So our only solution would be negative b over 2a, because we would be adding and subtracting 0 in the quadratic formula. And then if d is less than 0, we end up with a negative number under a radical, which of course doesn't exist up to this current point within the book. Try one. Determine how many solutions the quadratic has. If it has real solutions, use the quadratic formula to find it or them. 2x squared plus 3x minus 10 equals 0. Now let's do an example where we use the discriminant in an unusual way. On Endor, the height of the rock hurled by an Ewok can be modeled by h of t is equal to negative 9t squared plus 45t. You can sort of ignore the h of t as a concept right now. It's not really that important. All you need to know about that is that this quadratic will generate the height of the rock at some time t. So if we plug in a t, say t equals 1, then we'll know how high the rock was at time 1. A, when does the height reach 54 meters? B, when does the rock hit the ground? And C, when does the rock reach a maximum height? Okay, A, first of all, we're looking for when the height reaches 54 meters. Let's start with that. So if the height is 54, and this expression here represents the height, then we would just set this equal to 54 to find the time at which the height of the rock will be 54 meters. So we'll have negative 9t squared plus 45t is equal to 54. We can factor out a negative 9. And if we factor a negative 9 out, we're left with t squared minus 5t is equal to 54, like this. Now I can divide both sides by this negative 9 and end up with t squared minus 5t is equal to negative 6. And if I add this over, I get that t squared minus 5t plus 6 is equal to 0. We could factor, but instead I'm going to use the quadratic formula. When I use the quadratic formula, we get t is equal to negative b. Well, my b is negative 5, so we get 5 plus or minus the square root of b squared. So negative 5 squared is 25. Minus 4 times 1 times 6. So 4 times 6 times 1 divided by 2 times 1, which is just 2. So t will then equal 5 plus or minus the square root of 25 minus 24, which is the square root of 1, over 2. Now, the square root of 1 is, of course, 1. Then we have 5 plus 1 is 6. 6 divided by 2 is, of course, 3. So we have t is equal to 3. And 5 minus 1 is 4. And 4 divided by 2 is, of course, 2. So t equals 2. So we have these two t values for which the height is 54 meters. Part B. When does the rock hit the ground? Now, this might seem a little bit more complicated, but if you think about it in terms of height, when a rock hits the ground, what is the height of that rock? 0. And knowing that this expression represents the height of the rock, we would say that this expression is equal to 0. So 0 is equal to negative 9 t squared plus 45 t. Factor out the 9. We're left with t squared minus 5t is equal to 0. You can divide this over, and we get 0 divided by negative 9 is still 0. If you have 0 things and you divide it amongst 9 people, you get 0. Everyone gets 0 things. So we're left with then the quadratic t squared minus 5t is equal to 0. If we factor a t out, then we have t times t minus 5 is equal to 0. Now we have a zero product property here. T is one expression times the second expression is equal to 0. So either t is equal to 0 or t is equal to 5. Now this should make sense. When we throw a rock, or when an Ewok throws a rock, at time t equals 0, the rock is on the ground, or at least in this model, the rock is on the ground. At 5 seconds later, the rock is on the ground again. This is the second one. This is when the rock lands. This is when the rock hasn't been thrown yet. Part C, this is where we use the discriminant in an unusual way. So we're looking for when the rock reaches a maximum height. We know that this is a maximum. We also know that when it reaches its maximum height, it will only reach that height one time. Notice that when it reaches a height of 0, we have 2 t values. When it reaches a height of 54, we have 2 t values. Because you have that the rock reaches that height before it reaches its peak and after it's coming back down. So those are going to be the 2 corresponding t values. But when it reaches its maximum height, it will only reach it one time. So let's let h sub 0 be the maximum height. Then we have h sub 0 is going to equal to negative 9t squared plus 45t. Subtract this over, and we get 0 is equal to negative 9t squared plus 45t minus h sub 0. Now this is where we use the discriminant. We know that this quadratic is going to have a single solution. This means then that d is going to equal 0. So we know that the discriminant is equal to 0, which means that b squared minus 4ac is equal to 0, where our a is negative 9, our b is 45, and our c is negative h sub 0. So if we plug these in, we should get 45 squared minus 4 times negative 9 times negative h sub 0 is equal to 0. Now all we have to do is solve for h sub 0. We can subtract the 45 squared over. 45 squared is 2025. And then negative 4 times negative 9 is 36. And then times negative h sub 0 is 36 h sub 0. It's equal to 0. Then we add the 36 h sub 0 over, and we get 36 h sub 0 is equal to 2025. Divide by 36, and we get h sub 0 is equal to 2025 divided by 36. Now this reduces because 9 goes into both. So h sub 0 will equal 225 divided by 4. This is the maximum height right here. In order to figure out at what time our rock reaches the maximum height, we set our h equal to 225 divided by 4. Now if I subtract this over, then I get 0 is equal to negative 9t squared plus 45t minus 225 over 4, just like this. Now I can factor out a negative 9 again, just to make our number smaller. I'm going to use the quadratic formula again, but I'm going to make the number smaller by factoring a negative 9 out. We get a t squared minus 5t plus 25 over 4. And since this is equal to 0, I can divide the negative 9 over, and I end up with 0 is equal to t squared minus 5t plus 25 over 4. And then the quadratic formula will be t is equal to negative b, so positive 5 plus or minus the square root of b squared, 25, minus 4 times a times c. Should be easily seen that this is 0, specifically because we set it up to be 0 by using the discriminant is equal to 0. This is all divided by 2 times a, which is just 1, so 2. So t will equal 5 over 2. That's the time at which it reaches a maximum height. Next, we're going to talk about other types of equations that still use the quadratic form. Let's start with an example here. Okay, so if we have an example that looks like this, how do we solve it? Well, what we need to do first is combine the fractions, and I'm going to subtract the 4 over. You don't have to subtract the 4 over, but I would rather subtract it over than combine it with the other two fractions. Now, in order to combine these first two fractions, what we need to do is find a common denominator. So our common denominator is going to be a product of the denominators here, since they share no factors. Now, in a couple of steps, I'm going to subtract the 4 over. I'm going to multiply this one top and bottom by x minus 3, and multiply this one top and bottom by x. So we have an x minus 3, multiply top and bottom, multiply top and bottom by x, and I'm going to move the 4 to this side by subtraction. So it's not going to be a 4 on the right, it's going to be a negative 4. So we end up with 10 times x minus 3 over x times x minus 3 minus 12x divided by x times x minus 3 is equal to negative 4. Now I have a common denominator, so I can combine them. And I get 10x minus 30 upon distributing my 10 minus 12x all over x times x minus 3. This is still equal to negative 4. Now what I'm going to do is multiply the x times x minus 3 to the right, and I can combine the like terms on top. So I have 10x minus 12x will give me a negative 2x. So I now have negative 2x minus 30 is equal to negative 4 times x minus 3. And if I distribute this in, I get a negative 4x squared plus 12x. And I have a negative 2x minus 30 on the left. Now what I'm going to do is get everything on the same side, because we need it in the form of ax squared plus bx plus c is equal to 0. So if I move everything to the left side, I end up with 4x squared minus 14x minus 30 is equal to 0. Now, in order to do this, again, you can factor if you want to, But what I'm going to do is use the quadratic formula. So my a is 4, my b is 14, and my c is 30. You could factor out a 2 and divide it if you want, and it'll reduce your numbers a bit. But that's not necessary. So x is going to equal negative b, so 14 plus or minus the square root of b squared, which is 196, minus 4 times a times c. 4 times 4 is 16, and 16 times 30 is 480. And we also have a negative here, so this is going to turn into a plus. 4 times negative 30 will look like this here in the radical. Divided by 2a, which is going to be 8. 2 times 4 is 8. Then x equals 14 plus or minus 196 plus 480 is 676 divided by 8. The square root of 676 is going to be 26. So we get 14 plus or minus 26 over 8. So x will equal 14 plus 26 is 40 over 8. And x equals 14 minus 26, which would be negative 12 over 8. So x is equal to 5, and x is equal to negative 3 halves. And these will be your two solutions for this type of problem here, or for this example. Now, what you need to do in this type of problem is get the x's out of the denominator. That's the key. Because they're in the denominator, we can't really do anything with a quadratic. But once we multiply them over, we can. I want you to try one. 1 over x minus 1 plus 1 over x plus 2 is going to equal 5 over 4. The next thing that I'm going to talk about is a particular method to solve an equation, but it does create solutions that are not actually solutions to the equation. So first, what I need to do is define what I mean by a solution that's not a solution. An extraneous solution is a potential solution that does not satisfy the original equation. I'll give you an example of this. Generally, this comes up when we have to square both sides of an equation. So suppose we have something that looks like this. The square root of 5 minus x plus 1 is equal to x minus 2. We have something that looks like this. What we need to do is solve for x, but how do we solve for x when we have a square root in our problem? This is what's creating a problem. So what I would like to do is square both sides when the square root of 5 minus x is alone on its side. Because if we can square just this, then we can get rid of this radical. So subtract the 1 over, and we get the square root of 5 minus x is equal to x minus 3. Now I can square both sides. I need to make a note here though. Squaring both sides introduces extraneous solutions, and we'll see one in this example. On the left, we just get 5 minus x, because they're squaring a radical. On the right, we have x minus 3 squared, which will become x squared minus 6x plus 9. Remember, you square the quantity, so it's x minus 3 times x minus 3. Now we need to get everything on one side. Adding the x over gives us a negative 5x. And subtracting the 5 gives us a positive 4. 9 minus 5 is 4. Remember, we subtract 5 from both sides, and we add x to both sides. So we have negative 6x plus an x would give us a negative 5x. Now on the left, we have 0, because we canceled everything. Now to make this a little bit quicker than using the quadratic formula, I'm going to go ahead and just factor here. Two numbers that multiply to 4 and add to -5. That is -1 and -4. So this will factor into x minus 1, x minus 4. So x is equal to 1 and x is equal to 4. These are my two solutions. Now I shouldn't say solutions because of the method that we used. These are potential solutions. We have to verify these because we squared both sides. So if I plug in 1 to my original equation, I get the square root of 5 minus 1 plus 1 is equal to 1 minus 2. So is this true? 5 minus 1 is 4. The square root of 4 is 2. 2 plus 1 is 3. And 1 minus 2 is -1. So this is clearly not true. Very clearly not true. So x equals 1 is not going to be an actual solution. Now let's check x equals 4. Square root of 5 minus 4 plus 1, 4 minus 2. Now, 5 minus 4 is 1. 1 squared, the square root of 1 is 1. Then 1 plus 1 is 2. And we have a 4 minus 2 is 2. So x equals 4 does give us a solution. But notice that we have an extraneous solution. This follows from the fact that we squared both sides. Now remember, we subtracted the 1 over first. So let me do this in red so that I can show you what I mean here. If I subtract the 1 over, then I would have the square root of 5 minus x is equal to x minus 3. Now if I plug in 1 here, I should get the negative version on one side of the other side. So I'm going to get a positive 2 on the left, but I'm going to have a -2 on the right. 5 minus 1 we plug in our 1 and we get 5 minus 1. The square root of that is 2. Square root of 4 is 2. Is this equal to 1 minus 3, which is -2? Notice that this was the step in the process where we squared. You see how once we plugged in our 1, it gave us a negative version. But we got the 1 because we squared both sides. So if I square both sides, I would still have 1 would actually be a solution if I were to square both sides. But because we're going back to before we squared both sides, 1 becomes an extraneous solution. Definition? An equation with form aw squared plus bw plus c equals 0 is called a quadratic form. Now, we don't necessarily have to have a w or an x for us to have a quadratic form. I like to use w as my substitution variable. And you'll see what I mean here. So let's solve this equation. Suppose that we have x to the 4th minus 6x squared minus 16 is equal to 0. Now we have a quadratic form, just we have to use a substitution to get to this point. Let's say that w equals x squared. Well, x to the 4th is x squared squared. Notice that if we square both sides, we would have w squared is equal to x to the 4th here. So this would become w squared minus 6w minus 16 is equal to 0. And we have a quadratic form. We have the aw squared plus bw plus c is equal to 0. Then we would solve this just like we would solve any other quadratic. So we can either factor, or we can use the quadratic formula, or we can complete the square. Those are the three methods that we know so far. So let's go ahead and factor. Multiply. We're looking for two numbers that multiply to -16 and add to -6. And that's going to be 8 and 2. -8 and +2. Then we can go straight to the end because we have an a of 1. So we get w minus 8 times w plus 2 is equal to 0. Now, using the zero product property here, notice that we have a product of two numbers that is equal to 0. One of them must be 0. So we say that, well, w minus 8 might be 0, and w plus 2 might be 0. So w will equal 8, or w will equal negative 2. Okay, we are not done here. We are looking for x. We're not looking for w. So we need to resubstitute to solve for x now. X squared is equal to 8, or x squared is equal to negative 2. Well, x squared is actually never equal to negative 2, because no matter what we plug in for x, we're going to get a positive value because it's squared. So we can eliminate the second equation because it's impossible. Now the first one, we can just take the square root of both sides, and we end up with x is equal to either the square root of 8 or x is equal to negative square root of 8. And these will be my two solutions to this equation. All right, the last thing I want to talk about quickly is absolute value. We're just going to do an example here. And I'm going to make a note first that when the absolute value of x is equal to a number c, then x is equal to negative c, or x is equal to c. Notice that if I plug in negative c for x, the absolute value of negative c is equal to c, so this equation holds true. And if I plug in c for x, I get the absolute value of c is equal to c. So again, this equation holds true. So either of these solutions will work. So suppose we have the equation 3x minus 1 in absolute value is equal to 4. How do we go about this? Well, if we have the absolute value of something is equal to c, then we can split it into two equations where it's equal to positive c and negative c. Here we have 3x minus 1 will equal 4, or 3x minus 1 will equal negative 4. You do need to think about this for a second, though. You have to take a second and think about it. Don't just run through the process every single time. Absolute value will always give us a positive value. Right? You need to think about that when you see an equation like this to determine if it has solutions at all. We can add the 1 over. We just add 1 to both sides. Add 1 to both sides. And we end up with 3x is equal to 5, and 3x is equal to negative 3. Divide by 3. And we get x is equal to 5/3, or x is equal to negative 1. And if you plug both of these in, you'll get the correct solution, that they are correct solutions. So 5/3, this would be 3 times 5/3 will give us 5. 5 minus 1 is 4. The absolute value of 4 is equal to 4. So this solution works. If I plug in a negative 1, I get negative 3 minus 1 is negative 4. The absolute value of negative 4 is equal to 4. So this solution also works. I want you to try one now. Solve for x. The absolute value of 3x plus 5 is equal to 1. Now, here's an example of a similar problem where you might run into an issue. Now, if you just mindlessly go through the problem, the steps of the problem, and don't stop and think about the problem, then you're going to get the wrong answer. Again, remember that the absolute value of something is always positive. So if we have 2x plus 4, and we take the absolute value of whatever that is, we're going to get a positive number. But here we're looking for when the absolute value of something is equal to negative 4. So when is that true? When is the absolute value of something equal to a negative number? Never. So this actually has no solution. And you can immediately put no solution because you can see that we have the absolute value of something is equal to something that the absolute value can never reach. absolute value is always greater than or equal to 0, but -4 is less than 0, so this is impossible. That will be it for today. I will see you all in the next lecture.